Imagine trying to build a computer that runs on the very laws of reality that, we're still figuring out. A machine so delicate that the tiniest vibration or a single stray particle of heat could completely wreck its calculations. And no, this isn't some sci-fi movie. This is the absolutely monumental engineering challenge of building a quantum computer. Yeah, and this quote, it just nails it. We're not just clicking components together here. We are literally tinkering with reality at its most fundamental level. But that brings up a really important question. I mean, who are the architects brave enough to design and build something that pushes the absolute limits of what we know about science and technology? Well, they're called quantum hardware engineers. While the software folks are writing the amazing algorithms, these are the people who build the physical stage where all that quantum magic actually happens. They're kind of the unsung heroes making our quantum future a physical reality. All right, so where does their journey even begin? It starts with the most fundamental building block, the absolute heart of the machine, the qubit. And this is honestly the perfect way to think about it. You see, a regular computer bit is simple. It's a 0 or a 1. But a qubit, it can be both at the same time, which lets it hold an incredible amount of information. But just like that soap bubble, it is so fragile. The slightest little disturbance and poof, the quantum state is gone. Now, what you've got to understand here is that there isn't one single best way to build a qubit. It's a world of trade-offs. You've got superconducting qubits, which are pretty mature and you can scale them, but they need to be ridiculously cold. Then you have trapped ions, which are super stable, but they're slow. It's this constant balancing act between power, stability, and, practicality. So right now, the industry has kind of landed on two main ways to go. On one side, you have the superconducting qubits, which giants like IBM and Google are all in on. They're fast, you can scale them up. But on the other side, you've got trapped ions. They're slower, for sure, but they offer incredible stability. They can hold on to their quantum state for way longer. It's really the central tension right now, speed versus stability. So remember that fragility I mentioned? Well, the biggest enemy is just the world, especially heat. So the very first job for a quantum engineer is to build an impenetrable fortress against it. And this brings us to the main villain of our story, decoherence. It's basically the process where a qubit just forgets it's a qubit because of any interaction with the outside world. A stray magnetic field, a tiny change in temperature. It's this constant, relentless force that quantum engineers are fighting against every single day. So, how do you fight it? You create an environment so mind-bogglingly cold, it makes deep space seem warm and cozy. We're talking about 15 millikelvin. That is just a sliver of a degree above absolute zero, the point where all atomic motion is supposed to stop. And the engineering to get there is just wild. You can't just plug this thing into the wall. Engineers use something called a dilution refrigerator. It uses a rare isotope, helium-3, and in a super clever process, it basically evaporates those atoms to steal heat out of the system, creating this continuous cycle that gets you down to those unbelievable temperatures. Okay. So we've made our qubit and we've stuck it in the coldest place in the known universe. Now what? Well, now we actually have to talk to it. We need to build the nervous system for this quantum brain. And this is the engineer's toolkit. They use all this specialized electronics to send these perfectly timed microwave pulses, like tiny, precise nudges to control the qubits. They need chips that can give lightning-fast feedback and amplifiers that are so sensitive they can hear the faint whisper of a signal that tells them the qubit's state. It's a whole symphony of high-frequency electronics, all working in perfect harmony. But here's the thing. Even with that incredible deep freeze and all the precise control, our old villain, decoherence, is still trying to get in. So engineers need one final, incredibly sophisticated shield. And it's a battle on so many fronts. It's not just heat. It's stray magnetic fields. It's qubits accidentally talking to each other when they shouldn't. It's even microscopic defects in the materials themselves. Every single one of these can destroy a calculation in nanoseconds. So yeah, this is the billion-dollar question, right? If a single qubit is that fragile, how on earth can you ever build a reliable computer with thousands or even millions of them? Well, the solution is as brilliant as it is kind of counterintuitive.
You actually give up on trying to build one perfect physical qubit. It's maybe impossible. Instead, you build what's called a logical qubit. The idea here is you take a whole team of these fragile, error-prone physical qubits and you link them all together. They're constantly checking on each other, and by working as a group, they can act like one single, super stable and fault-tolerant qubit.
And this whole team-based defense system has a name? Quantum error correction. It's not some passive shield, it's an active, ongoing process. The system is constantly on the lookout for errors, identifying them, and fixing them in real time, all without messing up the main computation. It's basically the immune system for the quantum hardware.
But, and this is a huge but, for any of this to work, the physical hardware underneath it all has to be almost perfect. For the error correction to help more than it hurts, the error rate on every single little operation has to be below a certain point, and that number is less than 1%. It is an absolutely staggering bar for precision.
And that brings us full circle. The quantum hardware engineer. They're not just an engineer. They have to be a physicist, a material scientist, and really an artist of the ultra-cold and the ultra-precise. They're building the very foundation for a whole new age of computation, one where the biggest question might just be, now that we've built the impossible, what problems are we going to solve with it?